Hello, once again, Stats Nerds. Welcome back. I hope you had a good spring break. I really didn't. Just kind of hanging out here with my broken Achilles. But I'm sorry that I'm not back to join you yet. The man, is trying to hold me down. So I really hope to be back next week. It looks like that I will be. So I'm excited for that. Until then, we have one more section that we have to cover. That's section 3.3 on ordinary least squares regression. That's going to be our focus for the entire week. So let's do a really nice job with it. So before the vacation, we were talking about scatter plots, and we were talking about how to interpret and analyze them. And when we do that, we focus on three things: form, direction, and strength. Form means what shape does the scatter plot have? Is it linear? Is it quadratic? Is it exponential? Direction means does it have a positive or a negative association? And strength means how closely the points follow whatever pattern we said it had. And we learned about a way to quantify strength as long as we had a linear pattern. If we have a linear pattern, we can use the correlation coefficient, which we know is called R, to help us quantify the strength of the relationship. So I just want to remind you that we could have two pictures here. And one is a scatter plot that shows not so much spread, just a little bit of spread. And in that situation, we have a big correlation value. And here we have more spread, so we have a smaller correlation value. And I told you that, and yeah, maybe you got good playing that game and guessing the correlation values. I hope you did. That's kind of fun. Maybe this is like a 0.8. Maybe this is like a 0.3, something like that. But I also told you sometimes it's easier to try to imagine putting a line through the data. Wow, that's terrible. I'm going to undo that and try again. Put a line through the middle of the data, not much better. Put a line through the middle of the data, that's pretty good. Not museum worthy, but pretty good. And that can kind of help you get an idea about what the spread is. Now that's interesting because my guess is if I gave everybody the scatter plot on the right and told you put a line through the middle of it, we wouldn't get the same result. We'd get 16 people that all had slightly different lines. But the line that I'm talking about when I say try to draw a line through the middle of the data is actually what's called a line of best fit. And it's used to make predictions when we don't have information about data points in a certain section of the graph. The issue is it's really hard to just eyeball a line of best fit. And some of you might have heard about mathematical ways to find lines of best fit before, especially if you took Algebra 2. But they're wrong. So your teachers in the past probably told you, yeah, make sure there's an equal number of points above and below the line, and there should be 2 points directly on the line and things like that, but that's really not a good way to make a line of best fit. So we're going to talk in this course about the most common way of finding a line of best fit, which is called ordinary least squared regression, which I abbreviate to OLSR. It's been around hundreds of years. The early astronomers were using it, and now we're going to get to use it. So in order to help you understand how that works, we are going to take a quick example. So I would like you to type this data into your calculator, L1 and L2, and then make a scatter plot of that data so that you have both of these things here in front of you. What this data represents is students' ages and then their score on a problem-solving test. We see that the oldest kid doesn't have the highest score, so this kid here looks like the third oldest if we say that age here is on the x-axis. Has the highest score. And we see that this really young kid also has a pretty high score, higher than he probably should. So this is our score. Okay. So this is 10 data points, but the truth is there's actually 11 kids who took this test. I just happened to lose the 11th kid's information. Maybe that's happened to you. Teachers in the past have lost your test score, and yeah, I don't know if they ever found it. Maybe they just made up your score in the end. I don't know. I'm not saying they did, but it's possible. So what we're going to try to do right now is just make up the information for the 11th kid. So if you had to guess how old the 11th kid is, what would you guess? And if you had to guess what the 11th kid's score on the test was, what would you guess? At this point, I'd be calling on you for your ideas, and I'd be telling you they're wrong, and waiting, and then telling you maybe the best way to do it. So the best way to do it is actually to think about what is typical. So what I mean by that is we should think about, if we know nothing about the missing kid, what's the average age for all the kids in their sample? The best guess we could come up with would be the average. So if we had wanted to guess his age, we should do a one variable statistics L1, and when we do that, we would find out the average is 9. So my best guess for that kid's age would be 9. And my best guess for a score would be the average of all of the scores. So I would do one variable statistics L2, and I would find out that the average score is 8.47. So like if my life depended on it, if I had to put money on it, my guesses for his test score would be 8.47. This is probably not right. It's not a good prediction. I mean, there's a lot of possibilities for what the kid's age could be. There's even more for what his score could be. We just took what was typical, but that kid might not be typical. But this point, this X bar, Y bar point, is a really important point. It is the most typical age and the most typical score, and it's where your line of best fit, your ordinary least squared regression line, will be centered, is what I like to say. But I guess the right way to say it is that your ordinary least squared regression line is always going to pass through X bar, Y bar. But that point alone, one point alone, is not going to tell us everything we need to know about the line of best fit. We still need to know like the angle at which that slope passes through this point X bar, Y bar. So in theory, we need to know the slope of the regression line, the least squared regression line. And the way that ordinary least squares regression determines the slope is it seeks to minimize the vertical distance the points are from the line. It's really important. That's kind of the key fact. It doesn't try to make sure that half the points are above and below. It tries to make sure that the sum of all of the distances from the line we draw is as small as possible. So not every line will be as small, not every point will be as close to the line as possible, but in the aggregate, all of the points will be as close to the line as possible. And in order to do that, we need a definition. And that's the definition of a residual. So a residual is just a value. It's also graphically interpreted as a distance, and it is the observed value of y minus the predicted value of y. And if you think about it that way, what actually happened and what we thought would happen, the residual basically is how bad our prediction was, how badly we were off. This is what happened, this is what we thought would happen. The difference between them is how wrong we were. So I'm going to try to illustrate that graphically here. This point right here, so I just tried to eliminate all of the noise from a scatter plot. And what I tried to keep here was just one point out of a scatter plot. And it's not directly related to our example, it's just a scatter plot. And this is the actual value of the point right here. So this point has a y value if I just trace it across, and the notation we give for that is y sub I. It's not super important right now, but we'll use it again later. Y sub I. And this point I marked right here is kind of what it is what we predicted somebody, okay, if we go back to our example, so tracing down, somebody who has this x value for his age, we predict, according to our line, that they're going to have a test score that's here. And the notation we give for that is y hat, the predicted value of that person's score. This thing right here, this distance, is the residual. The residual, so every single point has a residual, because every single point is some distance away from the line. If it's on the line, then its residual is 0. This straight line distance right here is the residual. So I'm going to get rid of that squiggly I tried to draw. I don't like that looking at it. And just say this straight line distance right here is the residual. So in this case, we have a pretty big residual because that point is far away from the line. The actual y value for that point was pretty far away from what we predicted it would be. Okay. Now I said before that the ordinary least squared regression line tries to minimize the residuals. So to minimize the distance that the points are from the line. That's actually not technically true. It tries to minimize the sum of the squares of the residuals. And this is primarily because of like the negative issue we had when we were looking at standard deviation as well. Because if you take positive residuals and negative residuals and you add them up, you're going to get 0. So you square the residuals to turn all of the values positive. You might be asking, how would you get a negative residual? Well, a negative residual would simply be a point that's down here. Wow, why is that pen so big? A negative residual would simply be a point that's down here. Because in this case, the observed is smaller than the predicted. So the observed would be a smaller number than the predicted, so we get a negative residual. Okay, so this is just a fact to know that we're minimizing the sum of the squares. Okay. So the end result, once you get your line of best fit, it's going to be a linear equation, a line of best fit. I'm on highlighter, that's why. It's going to be a line of best fit. And the lines are always like in the form y equals mx plus b, but we use some slightly different notation here. So I already mentioned to you that y hat means the predicted value of y. So this is what the line tells us the y value should be, what our prediction is based upon the line. It's probably not correct because the point probably doesn't lie directly on the line. So we're going to have a residual. B here is the slope. It's kind of like in the m position of your y equals mx plus b. And the way you calculate the slope of an ordinary least squared regression line is you take the correlation and you multiply it by the quotient of the standard deviation of all of the y variables divided by the standard deviation of all of the x variables. You may have to do that, but you'll be given the r value, you'll be given the standard deviation of y, given the standard deviation of x, and then it's just kind of number crunching. But most of the time we're going to be using calculators to calculate our slopes. The a here in this equation is our y-intercept, and the way you could calculate the y-intercept without a calculator would be to take the mean of all of the y's minus the slope times the mean of all of the x's. And you may have to do that, just kind of plug in some numbers and crunch them. But again, most of the time we're going to do that on the calculator. It's really important to note and to understand that these values A and B you get when you do the regression on your calculator are from the sample. And because they're from the sample, they're sample statistics, which means that if we had a different sample, we would get different values for the slope, and we would get different values for the y-intercept. So those values are entirely dependent on the observations that you sampled. Different observations in your sample, different sample, you get different A's and B's. But you can think about it the same way we thought about all of the inference that we did a month ago, and that's that these are sample statistics that represent true value, that represent population parameters. And the population parameters that correspond to A and B are beta and alpha. So obviously this corresponds to B and this corresponds to A. In our next chapter that we're going to do, we're going to take a look at how we can determine the true value of the population parameter if we only know B. So we're going to be doing inference for the slopes of these regression lines. But we're not there yet, so don't freak out yet. But we'll get there. So the big question here, all of that stuff I said so far is important, really important to understand what regression does. The next important thing is how to come up with the regression equation. So here's the procedure. If you have an 84, you press Stat, Calc, and on your Calculate menu, you go down a ways, you're going to find linreg A plus BX. Be careful, there's also one that's AX plus B. That mixes up the lettering for the slope and the y-intercept, so try to choose this one. And you want to make sure that your x variable is in L1 and your y variable is in L2. You can ignore this part. And I like to insert this y1 here. The reason why is because it's going to store the regression equation that you come up with in y1, which is really great because then you'll be able to graph your regression equation and see how it fits the data. Just by pressing the graph button. Otherwise, you got to do a lot of rounding, and then you got to type in complicated equations into your y equals menu. So it's good to get in the habit of adding this y1 here. And over here, I give you the instructions for how you do that. Vars, yvars, function y1, and it will do that. And then you just click on calculate, and you get your regression equation. You got to have your hat, because this tells us that the y values can be predicted by using this equation, which means if I want to predict the score for a 10-year-old, all I'd have to do is say I'm going to predict that a kid who's 10 will get 6.402 plus, I have an idea. If I want to predict the score for a 10-year-old, then all I'd have to do is say that y hat is going to be equal to, oh, that shouldn't change to that. Y hat is equal to 6.402 plus 0.23 times 10. And I crunch all the numbers. Let me do that on my calculator here. 6.402 plus 0.23 times 10. And I would predict that a 10-year-old will get a score of 8.702. So this is how you use that equation. You use it to make predictions. If you have a TI Nspire, here's an 8-minute video that will tell you how to do this. Only the first few minutes, the last few minutes are stuff from the next section. So just go until you learn how to do the regression equation. So the most important thing is to understand what these values from your regression equation tell you. So our y-intercept was 6.402. That's a y-intercept, and it's the hypothetical value of y when x is 0. It's kind of funny. It's often not feasible. It often doesn't make sense, like in this example. Because when x is 0, that means we're talking about a kid who's 0 years old, a kid who's a newborn baby. And what this y-intercept would tell us is that a newborn baby would have a test score of 6.402. Yeah, doubt it. So it's good to know what it means, but it's really nowhere near as important as understanding the slope. The y-intercept is kind of, again, an anchor point for the line. It's just placing it in the right spot so that the slope is relevant. The slope is really what we care about, and in this case, that's 0.23. So what that means is a 1-year difference in age tends to correspond, on average, with a 0.23 point difference in test score. This entire sentence, it's kind of like the we reject the null hypothesis, or I am 95% confident that this. It's a sentence that you need to memorize the language of. It's super important that you say tends to correspond on average, because we're not saying that a 1-year difference in age means that a kid who's 12 is going to score 0.23 higher than a kid who's 11 every time. We're saying on average that's what tends to happen. But certainly there's going to be 11-year-olds who are smarter than some 12-year-olds, and they're not going to follow that pattern. So if you leave out this part right here, you're wrong. You have to say tends to correspond on average. A 1-year difference tends to correspond on average with a 0.23 point difference in test score. Okay, memorize how we interpret these things. That's really important. I wanted to also have you note that most of the time, our observed and our predicted are not equal, which means we're going to be wrong almost all of the time. The question is, how wrong are we? The only time when the observed equals the predicted is if our point from the scatter plot lies directly on the regression line. That's rare. Instead, so in this case, we could say that y sub I, it's the actual value of y for at some point, is equal to y hat. But that's really, really unlikely. Instead, the way you should think about this is that the actual y value, y sub I, is equal to what our regression line tells us, and that's this, a plus b times whatever x value we're interested in. That's our predicted value, that's whatever the regression line tells us, plus some error, some wrongness. So if we go back to our picture that we had before, here we have the actual y value, y sub I, it's equal to whatever our regression line tells us, plus however wrong we were, in green. So the combination of those two things, of our prediction and our error, add up to the actual y value. And that's the key point here, that the actual y value is equal to what the regression line predicts plus the error. I think this is a good stopping point. I think there's a lot to take in here from what I've given you and a lot of concepts to try to understand. So you might want to rewatch that video. Sorry, I'm probably giving you a headache. You might want to rewatch this video. You might want to read your textbook, section 3.3. I'm going to stop here, let you marinate on that, and my suggestion would be tomorrow, pick up, do the second half of this section. It's coming in your next video, where we're going to learn how to decide whether the regression that we just calculated is a good one or not. So I won't give you the homework assignment yet because you need the second half of it, but just let this sink in. Okay, talk to you soon.